Okay, so let's talk about 6.8 fluid pressure and force. This is the last kind of application, the last true application that we're going to do in in chapter 6. We do have one more section after 6.8, but 6.9 is not really an application section. In fact, I'm not exactly sure what it's doing with the rest of the material in chapter 6, but that's okay. It's still important information, so we'll cover it. But last bit of kind of application stuff, fluid pressure and force. So if a force of magnitude F is applied to a surface of area A, then we define the pressure, P, exerted by the force on the surface to be P equals F over A, right? So it's the force divided by the area over which that force is applied, right? That's called the pressure. So the units are going to be units of force divided by units of area. So if you're working with SI units, then it would be newtons over square meters. And newtons over square meters have a special name. They're called pascals, okay? If you're working with the British imperial system, then you would do pounds per square inch, or PSI, right? Even though it's called the British system, it's really only used in America, I think. But anyway, so that's that. So for example, suppose that the back of a swimmer's hand has a surface area of 8.4 times 10 to the negative 3 square meters, and that the pressure acting on it is 5.1 times 10 to the 4th pascals. Find the force that acts on the swimmer's hand. Well, if we know that the pressure is force divided by area, then the force should be pressure times area. Here we're given the area, here we're given the pressure. So the force is just going to be this times that, right? So I kind of wrote this out beforehand, but the force is just the area times the pressure, and that gives us the force of 4.3 times 10 squared newtons. Okay, so that's that idea. Now, when an object is submerged in a fluid, the force of the fluid on the object changes with the depth of the object in the fluid. And you've probably noticed that as you've swam or whatever. The further down you dive, the more pressure the water exerts on you, right? So the more you submerge something, the more pressure the object undergoes. And that's just because it's got all of the weight of the water on top of it also pressing down upon it, right? So the deeper you are, the more pressure there's going to be, right? So that's one thing that affects the pressure exerted on something, is its depth in it, submerged inside the fluid. The amount of force acting on an object submerged in a fluid also depends on the weight density of the fluid, right? So some fluid is more dense than other fluid, and so the more dense it is, the more pressure it's going to exert, right? So weight density is another factor. We have a symbol for the weight density. We use the Greek letter rho, which looks kind of like a little p, but it's the Greek letter rho. So the weight density rho of a fluid is rho equals W over V, where W is the weight of a fluid sample of volume V. And your book on page 394 has a list of some common of the weight densities of some common fluids, and so that page might come in handy for you. So just be aware of that. On page 394, as you're going through some of these problems, you might have to look up the weight densities depending on the fluid that you're working with. Okay, so the depth of the object and then the weight density of the fluid are going to affect how much pressure is acting on the fluid. So with that in mind, then, we can give a formula for the force and the pressure acting on an object that's submerged in a fluid. So the fluid force F and pressure on a flat surface that is submerged horizontally, right? And that's important. That's why I kind of squiggly underlined it. But if it's submerged horizontally at a depth h, then the force is rho times h times a, right? Where a is the area of the object. The pressure is just going to be rho times h, okay? So let me give you an example of this. So example 2 here says, find the fluid pressure and force on the top of a flat circular plate of radius 2 meters that is submerged horizontally in water at a depth of 6 meters. Okay. So let's see if we can do example 2. So in order to find the fluid pressure, we need to know the weight density of the water, rho. Here, sorry, I'm pointing to something that I just realized is off screen. But we need to know the weight density, rho, and we need to know the depth h. So well, as for the weight density, let's see. It's submerged in water. So we can go to that table on page 394 of the textbook and see, well, what is the weight density of water? And so the weight density of water in pascals, or sorry, not in pascals, but in newtons per cubic meter, is 9,810. And since we're working with meters, I think that's what we want to, that's the weight density that we want to use. So it's 9,810. Meanwhile, the depth, h, it says that it's submerged horizontally in water at a depth of 6 meters. So we would just say times 6. Okay. So you punch that into your calculator, you should get 58,860. And if you think about the units here, the weight density was given to us in newtons per meters cubed, and then the depth was given to us in meters. So when you multiply those together, these meters cancel one of those meters and leave newtons per meter squared, which is pascals, right? And that's good because pascals are a unit of measurement for pressure, so that's exactly what we want. So there's the fluid pressure. We also want the force, right? The force is going to be rho times h times a. So the force, rho times h times a, is 9,810 times 6 times the area. So in this case, it's a flat circular plate of radius 2 meters. So the area is going to be pi times r squared. Okay. So punch that into your calculator. 9,810 times 6 times 4 pi is, holy schmoly, that's a lot. 235,440 pi newtons, which would be how much? So I'll say that's approximately 73,900. No, I'm sorry. That's 739,700-ish newtons. Okay, so that's that one. All right, now so far you're probably thinking, well, what does this have to do with calculus, and what does this have to do with integration in particular? Well, notice again that these formulas work if the surface is submerged horizontally at a particular depth, because remember, the pressure is going to depend on the depth. Well, what if the object is not submerged horizontally? What if it's submerged vertically? Then the amount of pressure on the object up here is going to be less than the amount of pressure on the object down here. And so how do we calculate the force and the pressure on the object if it's submerged vertically instead of horizontally? So that's where calculus comes in. So if the object is submerged vertically, then what we need to do is split the object into horizontal strips and then approximate the force for each strip using the midpoint depth. Okay? So in other words, we'll take the depth of the middle of the strip, use the formula from the previous page, right? Use this formula to find the force or the pressure, just as an approximation, right? And then we'll add up all the approximations. Now, calculus comes into play when we take the limit as the change in depth for each strip. So I guess you could think of it like the width or the depth of each strip goes to 0. So if we allow the depth to go to the change in depth to go to 0, then we get an integral, right? And in fact, that's exactly what this fact is saying. So suppose that a flat surface is immersed vertically in a fluid of weight density P, and that the submerged portion of the surface extends from x equals a to x equals b along an x-axis whose positive direction is down. So here's a picture that'll help you to understand. So we've got this x-axis that's kind of pointing downwards, and here's a and here's b, right? So if you've got this flat object that's submerged vertically, right, and the sort of the top of it is at a and the bottom of it is at b, right? So for any x between a and b, like this x right here, suppose that w of x is the width of the surface. So w of x would be this width right here. And then suppose that h of x is the depth of point x. So h of x would be this depth here. Okay? So under all of those assumptions, the fluid force on the surface is the integral from a to b of rho times the depth times the width. Okay? And if you squint at that just right, you'll see that it's the same formula as the formula for the horizontal case, right? So for the horizontal case, the force was just rho times h times a. Well, the w of x times dx, if you are doing just an approximation, that's about the same as, the width of the width of the kth sort of slice times the height of the kth slice, right? Which is the area of the kth rectangle. So this area part A becomes wx dx up here. And then everything else stays the same. Height, density, right? And you just need to do this for all of the widths, I guess, between A and B, and then add them up. And that's why we're integrating. So that's the justification, I guess. It's not a formal proof. If you want a formal proof, you can look at the textbook, right? But that's the idea. That's why we're going to be integrating here to solve these kinds of problems. So let's take a look at a couple examples. So example 3 says, the face of a dam is a vertical rectangle of height 100 feet and width 200 feet. Find the total fluid force exerted on the face when the water surface is level with the top of the dam. Okay, so let's do this. So for example 3. Okay, so the face of the dam is a vertical rectangle with height 100 feet and width 200 feet. Find the total fluid force exerted on the face when the water surface is level with the top of the dam. So the water is right level with the top of the dam. So if I have kind of an x-axis or whatever, then this we can call 0 because it's right on the surface of the water. And this, I suppose, would be 100 because that's the height of the dam. Okay? So now, the other thing so now plugging stuff into our formula, right? So we know that the force is going to be the integral from A to B, so from 0 to 100 of the density rho. This is just water, right? Yeah, water. So same density that we used before, although this time we're working with feet. So maybe instead of using the density of fresh water, 9,810 newtons per cubic meter, I should use 62.4 pounds per cubic foot since I'm working with feet. So I'm going to use the the 62.4. Okay, so there's rho times the height. If you just take some generic like slice here at x, then the depth is x, right? So the height would be x, and the width, so from here to here, we'll say from here to here, is, well, that's uniform throughout, right? That's just 200 times x times 200 dx. Okay, so that's all there is to that. I mean, so let's finish the problem. It shouldn't be too difficult to challenge. Now 200 times 62.4 is 12,480 times the integral from 0 to 100 of x dx. So that's 12,480 times x squared over 2 from 0 to 100. So 12,480 times, 100 squared, that would just have 4 zeros, right? 1, 2, 3, 4. So what is that? 10,000. Oh, divided by 2 though. So I guess it should be 5,000. 5,000 minus, if you plug in 0, you're just going to get 0. So let's see. So 12,480 times 5,000 is, how many zeros? So 62,400,000. And that's in pounds. Okay? It's in pounds because we used the density that we used was pounds per cubic foot, right? So that's in pounds. Okay, so pretty straightforward. Let me give you another example. This one's maybe a little more challenging. It says a plate in the form of an isosceles triangle with base 10 feet and altitude 4 feet is submerged vertically in machine oil with the top of the triangle 3 feet below the surface. Find the fluid force against the plate surface if the oil has weight density rho equals 30 pounds per cubic foot. Okay, so we don't have to look up the density from a table, I guess, on this one because they give it to us. So let's see if we can do this. I'm going to draw a picture first and foremost. We've got an isosceles triangle. The base is 10 feet. The altitude is 4 feet, so the height of the triangle is 4 feet. But it's submerged vertically with the top of the triangle 3 feet below the surface. So we've got a situation kind of like this. So we've got like the surface of the oil up here, and then we've got the triangle kind of submerged down here. This is not to scale. That's okay. Right, yeah, the base is 10 feet. The height of the triangle is 4 feet. But it's submerged 3 feet down. So this depth is 3 feet. Okay, and we want to find the fluid force. Okay, so we might have to do some scratch work, but let's see what we need, right? So the fluid force is going to be the integral from A to B of rho times the depth times the width. Notice that this time we don't have a uniform width. Like if I take, let's say that I take this slice right here, right? That's going to give me a different width than if I took this slice down here, right? So the width is going to change depending on our depth. So let's. I'm trying to think of. I'm trying to think of the best way to do this. I kind of think. Okay, so if this is my x-axis, we'll say I kind of think that the best thing to do would be to say that this is 0. Right? So this height is 0. And if I take this slice, let's say to be x, I want to come up with a formula for the width of the triangle when the depth is, well, notice that the depth would not be x, the depth would be x plus 3 since we're 3 meters down. So that means this depth would be x plus 3. Right? So we're going to say h of x is x plus 3. But what's the width, right? What's the width? W of x. What's the width? Well, so the width is going to have to be, we can use some geometry here, right? So if I've got my triangle, I can say 10 is to 4 as W is to X. Right? So base is to height as base is to height. And this height, just from this point to there, is just x, right? It's just x. Okay. And then I can solve this for w. So if I multiply by x, then I get w equals 10/4 simplifies to 5 halves. So w equals 5 halves x. Okay, so that's w of x, right? W of x is 5 halves x. So I think I'm ready to plug stuff into my formula over here now, right? So I'm going to integrate from a to b, right, over the entire surface, so from 0 to 4, rho, which is 30, times h of x, which is x plus 3, times w of x, which is 5 halves x. So let's see, 30 divided by 2 is 15, and then 15 times 5 would be 75, and I'm going to remove that from the integral, or from the integrand. So then I'm going to have, I'm just going to have x plus 3 times x, so that's going to be x squared plus 3x. So I can integrate that pretty easily. And plug and chug, right? So 4 times 4 is 16 times 4 is 64, so this is 64 over 3 plus 4 times 4 is 16 times 3. Oh, 16 times 3 is what? 50 something. 16 times 3 is 48. Oh, I should have known that. 48 over 2. Oh, so that's just 24. Anyway, when you plug in 0, you just get 0 plus 0. Let's plug this into our calculator. So 75 times 64 over 3 plus 48 over 2 comes out to 3,400. And let's see, this would be in, this was pounds per cubic foot. We had an area and a depth, so that will get rid of the cubic feet. So this will just be in pounds. 3,400 pounds. Okay, and that's that. That's all I want to say for this section.